Scars tell stories, but in aging tissues, they sometimes won't stop talking. Behind every thickened patch of fibrotic tissue, whether in the lungs, skin, liver, or kidneys, is a cellular cast of characters that includes one particularly vocal group: senescent fibroblasts. Once seen as passive bystanders in tissue aging, these cells are now understood as active participants in chronic fibrosis, whispering signals that disrupt healing, stiffen organs, and trigger long-term dysfunction. But the plot has thickened because not all fibroblasts age the same way, and not all senescent fibroblasts are equally culpable. To understand how scarring goes from a protective response to a pathological process, we need to get specific about fibroblast subtypes and what kinds of senescence they bring to the table. Fibroblasts are structural cells producing collagen and extracellular matrix to support tissues and maintain architecture. When an injury occurs, they're recruited to help rebuild. In young, healthy tissue, this response is tightly controlled. Fibroblasts proliferate, lay down matrix, and then back off. But in aging tissues, something changes. Fibroblasts not only hang around longer than they should, they also adopt senescent phenotypes that drive persistent inflammation, abnormal matrix deposition, and mechanical stiffness. The result? Scars that don't fade, lungs that can't stretch, and skin that loses elasticity. This shift from helpful to harmful is subtle, but it hinges on the specific type of senescent fibroblast involved. Recent advances in single-cell sequencing and spatial transcriptomics have revealed that fibroblasts are not a homogeneous bunch. In fact, they exist in a surprisingly diverse ecosystem of functionally distinct subtypes, some inflammatory, some matrix-producing, others immunoregulatory. As tissues age or face repeated injury, certain subtypes appear more prone to entering senescence, and some of those senescent fibroblasts go on to become fibrosis architects. In diseases like idiopathic pulmonary fibrosis, IPF, or systemic sclerosis, for instance, researchers have identified senescent fibroblast populations that express both profibrotic genes, like TGFSS, collagen I and ESMA, and classic senescence markers, P16-INK, 4A, P21, SASS-GAL. These cells don't just build scars, they orchestrate them, recruiting immune cells and reshaping the surrounding microenvironment to sustain their own presence. What's particularly fascinating and clinically frustrating is that these senescent fibroblast subtypes often resist normal shutdown signals. In theory, fibrosis should resolve once the tissue is repaired. But in aging or fibrotic conditions, senescent fibroblasts seem to resist apoptosis, evade immune clearance, and perpetuate damage through the release of SESB factors. This creates a positive feedback loop: more inflammation, more fibroblast activation, more senescence, and ultimately more scarring. Importantly, not all senescent fibroblasts are bad. Some serve useful purposes during acute wound healing, limiting uncontrolled proliferation or promoting tissue remodeling. These helpful subtypes may be transient and less inflammatory, secreting matrix proteins in moderation or supporting angiogenesis. The therapeutic challenge, then, is not simply to wipe out all senescent fibroblasts, but to discriminate, to selectively target the pathological subtypes while preserving those that assist with recovery. That's where precision senotherapy comes in. Instead of using blunt force senolytics that clear all senescent cells, researchers are developing tools to identify and eliminate only the most fibrogenic fibroblast populations. AI-assisted analysis of gene expression profiles, protein markers, and spatial behavior is now being used to distinguish between different senescent signatures. For instance, some profibrotic fibroblasts express high levels of TGFSS-induced pathways and specific surface markers that could be used to guide targeted therapies. Others show metabolic dysfunction or resistance to phagocytic clearance, offering further angles for selective intervention. This strategy holds real promise for diseases like systemic sclerosis, where diffuse skin and organ fibrosis is currently managed with immunosuppression and symptom control, but not reversal. Or take IPF, where the lung becomes progressively stiff and gas exchange fails, largely due to aberrant fibroblast activity that won't shut off. A therapy that could specifically eliminate the senescent subtypes driving collagen overproduction, while sparing those needed for tissue integrity, could do more than slow progression. It could help restore function. There's also potential to apply this knowledge to cosmetic and regenerative medicine. Not all scarring is disease-level fibrosis. Some of it is the slow, cumulative result of microinjuries and age. Personalized anti-scarring therapies might one day be guided by your skin's fibroblast subtype profile. Are you more prone to inflammatory senescence or matrix-driven stiffness? Do your fibroblasts clear themselves efficiently, or do they linger? Answers to those questions could determine whether you respond best to topical senotherapeutics, microneedling, or biologics that modulate the senescence pathway without overcorrecting. In the end, studying senescent fibroblast diversity isn't just about understanding fibrosis, it's about redefining what it means to age gracefully at a cellular level. By listening to the subtle differences between helpful and harmful senescence, we may be able to rewrite the scar story entirely, not by erasing the past, but by making sure it doesn't calcify into something permanent.